this is where we're at. So this one was creating a sign chart for a rational function. And hyperbolas are the ones where we kind of go in line and we have to make tables for, and we prefer not to make tables. We'd like to know what the graph is going to look like without it, but sometimes that's not the case. And if we have a sign chart, at least we can get an idea of what's going on. You know, where's the graph always going to be negative? Where's it always going to be positive? And then maybe we use the asymptotes and say, hey, here's what I know about asymptotes. And I know that this region of the graph has to be positive, so maybe I can just make a sketch and I don't have to make the whole table piece. So this one says we're going to create a sign chart for a rational function. That's the key of this section is using those sign charts. Let r of x equal 2x plus 1 over, and I know they're saving themselves typing space, but we want to see it like this. That's what we want to see. We want to see, hey, here's our numerator and here's our denominator. So 2x plus 1 over the quantity x plus 3 times the quantity x minus 1. Determine the real number values of x that cause r of x to be 0, undefined, then make a sign chart to determine the real number values of x that cause r of x to be positive and negative. So they're trying to help us out a little bit because yesterday all we had to find was zeros. We didn't have any denominators. So what would make this 0? Well, that's f of x, or in this case r of x that we want to be 0, and that's the y. And the only way the y is going to be 0 is if this numerator is 0. So 2x plus 1 would have to equal 0. And usually we write that down and we go, oh yeah, it's going to be a negative 1/2. You subtract 1 and divide by 2. So negative 1/2, 0 would give us a 0. But because this does have a denominator, we have a new piece today where we have to say, okay, we know there are going to be some vertical asymptotes. And those vertical asymptotes are at the 0 of the denominator. So where is this going to be undefined if this is our denominator? Negative 3 and 1. So those are also some points that need to go on our sign chart as we look at, hey, where is this going to be positive and where is this going to be negative? Because there is that vertical asymptote that cuts it off, and we want to know where is this graph going to take place. So on the number line, negative 3, we go up here first, and then we'd have our negative 1/2 somewhere there, and then we'd have 1. And we want to know what's happening in the segments that those zeros and vertical asymptotes have chopped this into. We want to know as you go to the left forever, between negative 3 and negative 1/2, between negative 1/2 and 1, and then 1 on to infinity, what's going on with the graph. And like we did yesterday, we're just going to pick nice, small, easy numbers that we can use for this. So if this is negative 3, the next one over, next one to the left would be negative 4. And I just go right up here and ask myself, what's going to happen for each of these? And in this case, they are all linear factors. Well, if I put a negative 4 up here, that's definitely going to be negative up on the top. And on the bottom, if I put a negative 4 in this set of parentheses, this will be negative. And here, this will be negative. So I'm going to end up with 3 negatives here. Odd number of negatives, it's going to be negative. So this portion of the graph will be negative. Something kind of decent between negative 3 and negative 1/2. Probably negative 1. Negative 1 or negative 2, it doesn't make any difference, but negative 1 is a little bit smaller. So 2 times negative 1 plus 1, that's going to give me a negative up there. And then if I put negative 1 plus 3, that's going to be positive. And then negative 1 minus 1 will be a negative. And so that one with the 2 negatives is going to give us a plus. Between negative 1/2 and 1, favorite number, 0. 0. 2 times 0 plus 1, going to give us a positive. 0 plus 3, going to give us a positive. 0 minus 1, going to give us a negative. So 1 negative, odd number of negatives, it's going to be negative. Picking a number to the right of 1, 2. Put a 2 in here, we get a positive. A 2 in here, we get a positive. A 2 in here, we get a positive. So that portion of the graph will be positive. Now, one of the things I'll also do on my number line, which on your number line you're not supposed to do this, but I go up here and I think, okay, negative 1/2, 0. How am I going to remember that it's exactly 0 at that point? And I will put a dot there. And that's because I want to remind myself that was not a vertical asymptote. That was a 0. That's where it's at. And that helps a lot visually when you try to get to the graphic part. Right now, we could go ahead and answer their questions. It says, when is r of x going to be greater than 0? Well, we've got it right here and right here. Now, if it's greater than, should we include the endpoints? No. So we're going to say it's between negative 3 and negative 1/2 in union with 1 to infinity. And then when is it going to be less than 0? Well, same thing. We've got them right here. We could answer these questions. So we've got negative infinity to negative 3. Don't include them because it said less than, not less than or equal to. And then negative 1/2, 1. But the great part about this is now I can get a really good look at what this hyperbolic function will be. So I realize, all right, I have my vertical asymptotes. That's usually what we graph first, no matter what. So that would be at negative 3 and at positive 1. So there are my asymptotes. I got my little reminder down here that negative 1/2, 0 is a point on my graph. And I think, okay, what is my sign chart telling me? It's saying from that negative 3 vertical asymptote to the left forever, this graph is always going to be negative. Well, it has to approach the asymptotes, so it must do this. So that's going to happen. It's going to stay negative. And then, for this section in the middle right here, between my asymptotes of negative 3 and 1, I notice that the left portion of this is supposed to be positive and the right portion is supposed to be negative. Well, then it must do this. Has to. And then from 1 on, so our last vertical asymptote, it has to be positive. And from what I know about hyperbolas, we're going to have kind of symmetrical branches. So if one's negative and one's positive, like that. And we could certainly punch in the calculator and check, and this would be a good time to do that. So make sure you use an extra set of parentheses down here on the bottom. And let's see if our sketch is fairly accurate. What do we have here? So parentheses 2x plus 1. Parentheses divided by parentheses. Parentheses x plus 3. Parentheses. Parentheses x minus 1. Parentheses. Parentheses. We'll zoom 6. There it is. Well, it matches what our section has told us was going to happen, which is great because, again, the goal is to get everything you need from the math, not necessarily the graphing calculator. You don't want to use that first and then work backwards. You want to do what we know is right from the algebra first because we put stuff in wrong. It happens. We're human. Stuff happens. Down here in example 6, we've got solving a rational inequality by combining fractions. So this one says 5 over x plus 3 over x minus 1 is less than 0. And if we looked at this and thought about what we've been doing recently, we might say, you know what, let's multiply everything by the LCD so we don't have fractions. Bad idea. Here's why. When you work with inequalities, there's that one little extra piece to solving inequalities. What happens if you multiply or divide by a negative? You have to flip the sign. Now, we would only know to do that if we knew what numbers we were going to put in for x. We don't know that. So what we have to do is just combine this and solve it like we did the last one and figure out what's going on. So we're going to have to put these two little fractions together before we try and do any of the less than 0 piece there. So, we talked about this yesterday. What would we have to do? LCD. Got to find it. What's the LCD for those two? Yeah, it's both of them. X plus 3 and x minus 1. So this one's going to need the x minus 1 on the top and the bottom. And this one's going to need the x plus 3. top and the bottom. And we'll get 5x minus 5 over x minus 1 times x plus 3 plus 3x plus 9 over x minus 1 times x plus 3. And we'll see. Yeah, we've got a common denominator now. So we're going to put 5x plus 3x, which is 8x, minus 5 plus 9 is plus 4, over x minus 1 times x plus 3. And we want to know when is that less than 0. Now, the question becomes, okay, I can see I can factor 4 out. I can see that, but it's not going to cancel with anything on the bottom. So should I do that? The answer is yes. I mean, we're just going to be looking at signs. If you can use smaller numbers to figure out the signs, do that. The answer is also no. If you're looking at that and you're saying, well, it's just 8x plus 4, I can figure out if that's positive or negative without it. But I guess I kind of like the smaller numbers. So usually I will go ahead. And what it shows me when I'm grading your paper is you knew it was factorable. You just knew that you couldn't cancel anything out. And you have everything that you need right there. So now, we need to get thinking about our number line. And our number line, again, comes from the zeros and the vertical asymptotes. What's the zero of this one? Yeah, it's negative 1/2 again. We've got this 2x plus 1 up here. Again, it doesn't matter if you use the 8x plus 4 or the 2x plus 1. You're going to set it equal to 0, and you're going to get the negative 1/2, 0. How about our vertical asymptotes for this one? 1 and negative 3. All right, looking good so far. Well, those have to go on our number line. So let's see, in order we'd have, well, negative 3, negative 1/2, and 1 again. And again, like I said before, I'll take a look at this and say, you know what, I don't want to forget this is my 0. That right there. And then we just figure out, going to be positive, going to be negative, what's going to happen here. So, something to the left of negative 3 that would be good. Negative 4. So we put a negative 4 up here. It's going to be negative. Negative 4 here, going to be negative. Negative 4 here, going to be negative. So what do we know about the sign from negative 3 to the left forever? Don't lip sync. Tell me what it is. Negative. All right. Nice number between negative 3 and negative 1/2 that you're willing to work with. Negative 1. A negative 1 up here will give us a negative. A negative 1 down here will give us a negative. But a negative 1 in here is going to give us a positive. So what's happening? Nice number between negative 1/2 and 1. Yeah, absolutely. Use the 0. 0 plus 1 going to be positive. 0 minus 1 going to be negative. 0 plus 3 going to be positive. So what are we looking at from negative 1/2 to 0? Negative. Number to the right of 1 that you're willing to use. A 2. That appears in some space. So that's going to be positive. 2 minus 1, that's going to be positive. 2 plus 3, that's going to be positive. So what do we know is happening out there? Positive. Well, what are we supposed to do with this? Say when it's less than 0. So, way back up here, all the way to the beginning, you can look at it. You can say, hey, this is what I'm trying to do, less than 0. But if you're writing that as you go, thank you. You can absolutely see, you're supposed to see when is it less than 0. Are we going to include endpoints if it has to be less than 0? No, we're not going to include endpoints again. So, where are we less than 0? Union with, do we have another negative part? Where to where? Negative 1/2 to 1. There it need to see the graph for this one, but you would see exactly what we have going on in our sign chart here from the last problem. So it's just one of those things where it really helps us with graphing hyperbolas without having to overthink them and put in all kinds of tables on stuff. So now, here's what I need to know, because I know it doesn't separate this for our objective here. But I really want to know, how do you think you're doing on hyperbolas, on just hyperbolas? Using the zeros and the vertical asymptotes. Okay, so some of you are saying a little bit more practice would be good. Well, we're not done. We're kind of done with hyperbolas, but we're not done. Because we're also going to solve some other inequalities. Weird looking ones. Solve an inequality involving a radical. Ooh, that's interesting. Okay. Solve the quantity x minus 3 times the square root of x plus 1, which is greater than or equal to 0. Use a sign chart. Check your solution. We're going to check it graphically. And the first thing I think of is, well, this has a restriction on the domain. Just like I think about vertical asymptotes whenever I'm thinking about my fractions, I have to think, I can't use all real numbers for the square root of x plus 1. I can't do that. The square root of x plus 1 has to be greater than or equal to 0. And in order for that to happen, x plus 1 is going to have to be greater than or equal to 0 in order for us to find this. And that's just by squaring both sides. Well, then you realize, hey, I'm going to have to subtract 1. So x is going to have to be greater than or equal to negative 1. So, on my number line, I've got negative 1. And it would be incredibly silly of me to put in negative 2 into this function, because my domain is x has to be greater than or equal to negative 1. So right now, I'm going to write over here, undefined. So I don't try to put some numbers in over there. Can't do those. It is undefined. Yeah, that looks really bad trying to write sideways. That just doesn't look like undefined. So that's out of the way. Then I think, okay, even though it looks weird, they always have to find the zeros. So what's the 0 for this little mess? 3. All right, so 0 at 3, 0. And if I do put my negative 1 in there, well, that gives me 0 as well. All right, so I need 3 on here. I need to remember, I'm going to hit there, I'm going to hit there. Well, I need to know where you're talking positive or negative here. What is this weird thing going to look like? So between negative 1 and 3, give me a nice number you'd be willing to use. 0. 0 minus 3. Ooh, that's going to be negative. 0 plus 1, the square root of 1, that'll be positive. So that's going to be interesting. Number to the right of 3. A nice number to the right of 3. Yeah, let's put a 4 in there. Let's see what happens. All right, if we put a 4 in here, this is going to be positive. And this has to be positive. Aha! Interesting. So I wonder what this looks like. Well, it has a square root in it. You guys remember what square roots look like? Draw a square root graph in the air form in front of you. And it does have a curvy thing. So if I had to take a guess, because this is negative, I'm thinking it's going to do something like that. Because it's got to have the curvy thing from the square root. Well, let's plug it in and see. See if it matches what we know. Y equals parentheses x minus 3 parentheses second square root of x plus 1. And uh-oh. There's a gap. Your calculator shows a gap. Color calculators, you have more pixels. No gap, right? Yeah. Here's a better than that. that's graph or error. We have to know, yeah, -1 is where this thing starts, and then go from there. The newer ones, they have no fixes. That's what it's doing. And that matches what we know from our sign chart. Now, we're not quite done. Supposed to tell when this is greater than or equal to 0. Oh, greater than or equal to 0. Interesting. Didn't we have 2 spots where this was equal to 0? So we're going to have to mention the -1. And you could use square brackets for that one too. But where else is it greater than or equal to 0? 3 on up. Should we include the 3? Oh yeah. That kind of looks awkward with the Richard Nixon brackets, doesn't it? So you could use square brackets on that too. But either way, it's set notation and it'll work. So there's our answer. But we should check and make sure, hey, the graph that we see is going to match what we want on our sign chart. Well, this one looks even more interesting. Crazy absolute value piece. What? All right. Well, let's see what we can do. We always start by, anything that gives us zeros or anything that would make this undefined. And I see that this one has division, so obviously we should be able to find a vertical asymptote for this. What's the 0 for this one? 2. Yeah, okay, we've got a 2, 0. We'll make that happen. Where's that vertical asymptote going to be? Yeah, -3. And if you're thinking, but it has absolute value, well, we'll think through it all the way. It's still going to be 0 on the denominator if we put that up there. So that's what we have for our sign chart so far. We've got a -3 and a 2. Interesting. Well, our 0 is a 2. Put that on there. And let's see what this weirdo graph is going to look like. So, oh man, I wish they would have all ended up with a -3. So we're always using -4. That's okay. It's an okay number. You can go back to the original and say a -4 up there is going to make that negative. Okay, no matter what. What's our denominator always going to have for a sign? Always. So that's good. -1. Nice number between -3 and 2 you're willing to work with? Yeah, 0. Well, that's going to be negative up there. And we know the bottom is always going to be positive. So what's our sign for -3 to 2? It has to be negative. And then to the right of 2, definitely positive, definitely positive. So it's positive. Let's see here. So what does this mean in terms of our graph? So we've got a vertical asymptote right there. And we have a 0 at 2, 0. And this is telling us to the left of -3, everything's going to be negative. Okay? Like that. From -3 to 2, it's going to be negative, then it's going to cross and become positive. Well, asymptotes are asymptotes, so it should do something like that. Now, normally I would say that's going to worry me because this is a hyperbola and it should have 2 symmetrical branches. No, not when there's absolute value involved. Absolute value, you have to just throw it in the off the window. So that's what we think it's going to look like as we graph that out. Not so much that it's going to be a horizontal asymptote as I know the sign is guaranteed to be negative. So it's a sketch. Yeah. With this, we haven't really covered how do you get the horizontal asymptotes and all that kind of mess with absolute value. So we just use this sketch to go. And then we finally need to answer the question, which was, when is this going to be less than or equal to 0? That equal part is something we want to pay a lot of attention to. So let me move that up just a little bit. So where is this less than or equal to 0? Up to the -3? Do we include the -3? Can't. It's a vertical asymptote. Where else? -3 to 2. Okay. Do we include either one of those? The 2, because it did have the equals. We can't include the -3. That was an asymptote. But we have to include the 2 because that was a 0. So that was not quite as weird as the one with the little 1 sitting there all by itself. But yeah, if we graph this one, oh, I should remind you guys how to graph absolute value. You probably need that skill. MCA's, ACTs, you need to know how to do the absolute value piece. So y equals parentheses x minus 2 parentheses divided by, and then it's under math, numbers, and it's number 1. And we have x plus 3. So there's the absolute value of x plus 3. And there it is. Pretty close to the sketch. Just by using what we know about positives and negatives and all of that. I'm definitely, my slope is a little higher than it should be here. It's kind of come back. But this wasn't about necessarily getting a whole graph. It's about getting a good sketch. So we got a pretty good sketch. All right, so now we've seen all kinds of wonderful equations, or inequalities, I should say, and we have a couple of word problems to take a peek at here. The good news is they're word problems we've already seen. We've already done these word problems before. We're just going to change the way it's worded so that it's not, here is your maximum, here is your minimum. It's not equals anymore. It's, hey, we want at least this, or we want at most this. And that's when you start seeing inequalities, is when you say at least or at most. So Dixie Packaging Company has contracted with another firm to design boxes with a volume of at least 600 cubic inches. Squares are still going to be cut out of that box, or I should say that cardboard. And this time we've got 20 inches by 25 inches. You only have to cut out the little corners out of that box to do that. So, volume of a box. I mean, we've dealt with this before. Like it says, you're going to take the cardboard, flaps folded up to make an open box. So we're going to have 20 minus 2x, 25 minus 2x. And what's the height of that box going to be? X. At least 600. So would 610 be okay? That's at least 600, so we're going to definitely use greater than. Now why can we use equal to? Is 600 at least 600? Yes. There it is. Now, we already talked about how solving inequalities is a little strange, because if you multiply or divide by a negative, you have to switch the sign, and we don't know what we're going to put in for x here. So what we want to do with this one is just turn it over to the graphic calculator and say, you know what? I need to see when this y sub 1 hits 600. Because what I care about is when it's 600 and above, because it said at least 600. And that's what we want to give them for information. And that's why I brought this thing up here today. So that I think with the other ones, people that are just watching the video will be okay, but not with this one. I think they need to see it. And you could find the zeros. You could do it that way. Now, that's going to be a little tougher because you'll have a harder time figuring out what your window should be if you do that. So these are a little easier if you just leave them as is and go for it. So what do we need? We need parentheses or 20, well, I put the x in front of here. X, parentheses, 20 minus 2x, and 25 minus 2x. Parentheses. Yep, and then we had at 600 as the cutoff. Oops. There we go. So, window. Now it was 20 by 25. So if our x in 20 minus 2x, if we put in a 10, now we have a volume of 0. So basically 0 to 10 should be pretty safe for those x's. But we know we want to see 600. So maybe 650. If I really wanted to see the top of this thing, I'd say, you know what, I should go a little bit higher with my windows. It doesn't necessarily matter that we see the whole thing, but just because we're going to say at least, I want you to see this. I'm going to go with 750 just to be certain I see it. Still didn't get the whole top. A little bit better. So at least 600. We said is greater than or equal to. So that would mean they could pick anything from here to here. Well, what we need to know is what's the here to here? You know, especially since it said at least, and we said we have to include that because we have that equals bar. We need to know what those are. So let's use old Blinky there and let's find the intersection. Second trace. 5. Where are you, Blinky? You're at 5, 750. Well, fine, we'll do the right one first this time, Blinky, since that's where you want to be. Over here, please, Blinky. That one, and there we are. So 6.159. Transposing a couple of numbers there. Give us that one. And second trace, number 5. Yeah, I figured I'd have to go to the computer for that one. That's the one piece that just doesn't work very well on this thing. Come on back down, Blinky. There it is. Enter, enter, enter. 1.659 with rounding. So back to the paper. And when we graphed it, looked like that. 600, looked something like that. And the two numbers we had were 1.659 and 6.159. Interesting set of numbers there. So are we including those? Yeah, we had our equals bar. Anything between 1.659, including 1.659, and 6.159, including 6.159, will work. That'll give it a volume of at least 600 cubic inches. So, not really a new word problem. I mean, we've done several of these now with the volume of the box. Mostly just applying this with what we know about our inequalities. And the juice can, the tomato juice. So, this example says, designing a juice can revisited. Stewart Cannery will package that tomato juice in the 2-liter, and remember it was really important that we knew that was 2,000 cubic centimeters cylindrical cans. Find the radius and height of the cans if the cans have a surface area that is less than 1,000 square centimeters. Okay, so the issue with this one was we've got volume, and then we have to use that together with surface area. So important that we remember that the volume of that cylinder is pi r squared h. We had a 2,000 in here. And because the surface area formula has both an r and an h in it, we had to substitute. But let's hang on a second so everybody can see, remember what we were doing with this. Surface area formula, 2 pi r squared plus 2 pi r h. So there's our surface area formula right there. Now, we can't graph this on a graphical calculator. It has 2 variables. So just like we did before, we're going to solve the red one up here for h, 2,000 divided by pi r squared equals h. So that we can substitute it into that monster right there. 2 pi r squared plus 2 pi r times 2,000 pi r squared. And then it said, surface area that is less than 1,000. Oh, we didn't have to do anything about that at all. Less than 1,000. No at least or at most or anything like that we have to think about. It's just like that. Now I wouldn't punch that in. I would simplify just like we did before. We'd say, okay, I've got the pi's are gone, one of the r's are gone, 2 times 2,000 is 4,000. 2 pi r squared plus 4,000 over r is less than 1,000. And then again, because we want to avoid any problems with inequalities, solving inequalities by switching signs, yeah, we would just push this in just like we did the last one. Take a look at what this monster is and see where that intersects the 1,000. So let's put all of this up. And let's see, we had 2 pi r squared, 2 second pi x squared plus parentheses 4,000 divided by x parentheses. And no. Well, when we did this problem before, yeah, we said about 10 centimeters was probably a pretty good radius, so we should be good there. But now we have to be able to see that 1,000, so I'll maybe go with 1,200 just to be absolutely safe this time. My values? Well, look at that, it's upside down. That's okay, because it said less than 1,000. So if we want less than 1,000, we want the stuff that's below anyway. So we want that right there. Should I put dots where it intersects? We don't want those. It said less than. Now we need to know where they are so we can write our interval notation, but we're not going to use those points. We want to go between those two. So second trace, number 5. Where are you at, Blinky? Right side first this time. Sounds good, Blinky. We are at 4.619. And then we'll probably have to go to the computer for the other one. Oh yeah, Blinky's going to sit right there. All the way over to the right. Come on, Blinky. You can do it. You can make it. Little engine that could. All the way over there. Come on, come on, come on. All right. Enter, enter, enter. 9.655, rounding to 3 decimal places. And then we just need to remember we're going to use parentheses with those. It said less than. It didn't say less than or equal to. So we've got 4.619 to 9.655. And yeah, it said enter your graph into the G, so we probably better make a little sketch over here. We had our graph kind of hanging down a little bit there. And we had our 1,000 about there. And this was the portion So there it is. So the last part of our objective was these two problems right here. Solve real world problems using inequalities. Cat's question. Oh, did they want both? Oh, we just found the radius. So now we'd have to plug that in and find the height. Good catch. I don't think they caught that last year because I don't have a note here about that. Yeah, we'd go ahead and plop these in. Good catch, Chance. So we'd have 2,000 divided by, parentheses, pi times 4.619 squared. Yes. Right. 29.839. And second enter. You know what? I bet we ran out of time last year. That's probably why. 6.829. So I probably better label this radius. Height. And we're good to go. Yeah, with intervals we don't necessarily do that. And you know what? With this problem especially, Hannah brings up another good point. You probably would want to write a sentence. I mean, especially if this is something a company has asked you to do, you're going to write a sentence that says the radius should be between 4.619 and 9.655 centimeters. And the height should be between 6.829 and 29.839 centimeters. So somebody that doesn't know a whole lot of math could look at it and understand what's going on with that problem. So 43210 me on the two wordy problem things that we just did. Real life applications. Okay, so some people kind of signal in a 2.5 there. Yeah. And it's practice. I mean, that's how we get there. And math practice makes perfect. So there we go. 27 to 42 multiples of 3. 27, then you do 30, then you do 33, etc. And then 43, 45, 49, 58, 59, 61, 62. You have to take a picture if you want to. Otherwise, I'll make sure I get that.